Welcome back to Advent of Code. Sorry, need to move the mic. Advent of Code 2018, day 19. The final 7 days of Christmas. No, not 7 days of Christmas. 7 days preceding Christmas. So this one is about assembly code. I think we had a sneak preview of it before. Yay, we love our assembly code, don't we? I don't mind it so much, but it's often quite difficult, actually. Alright, let's see what we got here. Go with the flow. With the elves well on their way constructing the North Pole base, you turn your attention back to understanding the inner workings of programming the device. You can't help but notice that the device's opcodes, so it's referring to day 16, right, don't contain any flow control, like jump instructions. Oh, great. This is what complicates things. The device's manual goes on to explain. In programs where flow control is required, the instruction pointer can be bound to a register so that it can be manipulated directly. Okay. Set R, set I can function as absolute jumps. Yeah. But is it specifically register C that we're... Yeah, it is. Okay. Wait, no. It's whatever the third parameter is, right? Yeah, okay. And other opcodes can cause truly fascinating effects. Oh man, that scares me. When they say truly fascinating effects, it's going to be complicated. This mechanism achieved through a declaration like IP1, which would modify register 1 so that accesses to it let the program indirectly access the instruction pointer itself. What was IP again? Oh, this is a new command. Should zoom in a bit. Modify register 1. There are 6 registers, 0 through 5. The 5 not bound to the instruction pointer behave as normal. So before we had what? 3 registers. No. Doesn't matter. When the instruction pointer is bound to a register, its value okay, so IP sets which register is being used currently for the instruction pointer. Alright, makes sense. When the instruction pointer is bound to a register, its value is written to that register just before each instruction is executed. What? Yeah, okay, fine. And the value of that register is written back to the instruction pointer immediately after each instruction finishes execution. What? No, I'm lost. What? What does this sentence mean? The... When the instruction pointer is bound to a register, so we've got the instruction pointer. Is bound to something, alright. So the instruction pointer is actually separate. So the 5 not bound to the instruction pointer. Uh-huh. Its value. What? I'm so lost. What do you mean its value? The value of that register. It's... No. So the instruction pointer is a separate variable. Okay. So if we bound it to a register, we copy that value to the register just before each instruction is executed. What does that mean? So we actually execute that instruction. And then whatever the result of that register is, whether or not it changes, is copied back to the instruction pointer. Fine, alright, fine. Move to the next instruction by adding 1 to the instruction pointer, even if the value in the instruction pointer is just updated by an instruction. I see. So the binding isn't permanent. It's just you execute 1 iteration of that instruction. Okay. Instructions must effectively set the instruction pointer to the instruction before the one they want executed next. Before. But that will execute the instruction before. Not the one... What? Don't know what that last sentence means. Alright, this is a tough read. Okay. The instruction pointer is 0 during the first instruction, 1 during the second, and so on. What? No, the instruction pointer is controlled... is... It's 0 during the first instruction, but it might not be 1 during the second. Because it could be changed by the instruction itself, couldn't it? So why would it unequivocally be 1? It could be 1, or it could be anything else. starts at 0. I agree with that. Why would it be 1 during the second? Because it says up here that this could happen. The value of that register is written back to the instruction pointer after each. So this is wrong, I think. It's not 1 during the second. We don't know what it will be during the second. Okay, whatever. Alright. IP0. Alright, let's follow this example because I'm not really confident with this. So instruction pointer set to register 0. Alright. The values of the 6 registers for the instruction itself and after. Alright, so okay, fine. IP equals 0. So we're gonna execute instruction 0, which is it's the first is IP 0 itself, isn't it? Or is this not, does this not count as an instruction? What? Oh, maybe I've misunderstood that. Oh. That line there is not an instruction. IP is not an instruction. Let me check whether I... Declaration. Okay. Alright, fine. So we declare that the instruction pointer is set to 0 to begin with. Alright. So we execute instruction 0. That is set 501. So don't remember what the instruction does exactly. Let's have a look. Set. It's set I. Store A into C. Alright. Store A into C. So 5 goes there. Alright. Then whatever is here in instruction gets copied back to the instruction pointer. So IP is set to 0 again. Then you increment IP to 1. Got it. Alright. Now we execute this instruction 602. So 6 is copied to 2, right? 1 is copied to IP. IP is increased by 1. Now we do add I 010, and that is A plus B and put it in C. All right, so it'll be 2 plus oh yeah, I forgot to mention also that the IP gets copied into back into 0. Okay, so IP gets copied there, so now that's 2. Those stay 5 and 6. Now we take 0, we take 1, add them together, 7, and put the result in C. In the first. Wait, what? Had I? Oh, it's register A and value B. Okay. Register A, 2, plus value B, 1, equals 3. Put that in 0. Then we copy that to the instruction pointer. IP is now 3. Then we increment. Okay, wow. You have to do the steps really precisely. So IP will actually end up 4. Alright. Do I keep reading? Yes, I think so. Set R. So set R is copy register A into register C. So 4 gets copied here, alright. So the 5 gets copied here, so that ends up here, 556. Then IP gets set to 5, then increment it to 6, so on. Alright, I get it now. What value is left in register 0 when the background process halts? I hope it halts in a reasonable time. Otherwise, we're going to do some annoying investigations, which are quite difficult when it comes to assembly code, because you have to work out the semantic meaning of this stuff, like whether it's calculating prime numbers or something weird like that. Okay. I don't think it will be like that, because it's even just running it is a lot of work. We have to... Okay, remember we've done some code for 60. So we have to... We've got our old code here. All right. But this time we don't have an encoding scheme. Okay, fine. So to find it, so we want to copy that mess. We don't need any of this other stuff. Okay. All right. Now, alright, tokens equal line dot split if tokens, it's going to start with hash dot starts with hash. Then, okay, so we need a variable which is IP instruction pointer equals, starts with 0. Well, actually, it should start with none. No. No. Instruction pointer and the binding are two different things. So IP equals 0. IP binding equals none. So it's set by that number there. So, all right, register 2 is going to be the binding. Okay, got it. Okay, now we need instructions. Okay, so it's going to be... So take the first parameter and then int. Next one, int. Next one. Okay, that fulfills the filling of the instructions. Now, IP equals 0, IP binding is set to 2, but whatever it's set to. We want the instructions, so we want to say while IP, so it's going to be less than or equal to 0. So while we're not outside of instructions, all right, here are the steps. So whatever is an IP gets copied to, oh, do I have the registers? Okay, so the registers is how did I define it? But also, I think I need to zoom in. I did it like this. Maybe it should be a list. Because we're going to have to be modifying it repeatedly. So it's 0. So it's how many? 6. Okay, so whatever is an IP gets copied to regs IP binding equals IP, all right? Then regs, okay, so let's define that to be regs. We don't need to do that. We'll call it reg. We don't need to return anything, just modify it in place. Okay, so then we perform instruction. So it's going to be opcode, so it's going to be so the instruction we want equal. Oh man, it's called. Let's see. I'm running out of variable names. Okay, let's say x equals instruction IP. Alright, so we're gonna have x0 yeah, okay. x1, x2, x3, and regs. So we perform the instruction. Then, whatever is in IP binding gets copied back to IP. And then IP plus equal 1. Is that it? And then what? What's in register 0? Okay. Alright, see if that runs. If tokens 0 starts with hash, so tokens, what? Oh, why have I... Do it like this then. Got an infinite while loop there. Alright, now it's... Okay, the fact that it terminated is a good sign. Well, it was bound to terminate, even if it made a mistake somewhere, probably. 1728? Interesting numbers here. What does it mean? 256 suggests something is doubling, maybe. And we've got 995, 995, 994, and a 1. Alright. 1728. Correct. The new background process immediately spins up in its place. It appears identical, but on closer inspection you notice that this time register 0 started with the value 1. What value is left in register 0 when this new background process halts? Oh no, I don't like the look of this. Register 0 starts with 1. It's gonna take forever, isn't it? What's special about these numbers? Alright, just try it then. So start with 1. And we just do it as before. It's not gonna finish. Alright, so what the heck is going on? Well, don't make me read all this assembly code. Oh man, my machine fan is... I'll give it a minute or so just in case we can actually do it, but... Alright, stop. Okay, how about... see what the regs look like every 100,000. What the heck is going on here? Every 10 million? It looks very stable. So, what are they asking again? What value, what the first parameter is going to be when this holds? What do we think is happening here? This number here is not changing. 10551,394. Hello? So we had 4-1, now we've got 9-2. We've got 4-3. What the heck? Is there a pattern here? 9-4. So we had 4-1, 9-2, 4-3, 9-4. So this one's going 1, 2, 3, 4. This one's going 4, 9, 4, 9. This one on the left is... adding, like... 10,000s at a time. I don't know exactly what it's doing. So that added 50,000 there. Well, no, more. 1, 2, 120, 125,000. 1, 2, yeah. It's a strange pattern. Then here we were adding from 69 to 194. 5, 125. So still 1,250,000. Interesting. Where does that number come from? It's every million, every 10 million. We're adding 1 million, 1.25 million or something. Now it's gone up to 10. So it was 0, then it went to 1, then 3, then 10. Oh, I don't think we can work this out just from this alone. So that's definitely going 6, 7, so on. This number is never, these last two numbers are never changing, I think. This is alternating between 4s and 9s. So it's counting something. Something that happens. I see the pattern, so I'm gonna have to look at the code. I hate this. Could it be something to do with the digits? It likes these 4s and these 9s. 4 and 9 are the last two digits of this number. Is that significant? Why is it alternating between 4 and 9? For I don't know. Does this number on the left ever exceed the number on the right? I think it's trying to... No, it doesn't. So it's trying to compare. So this second number seems to be rolling, counting from like 1 to that number every time. And during the course of that, it's counting whether or it's like counting factors or something, like whether... What I don't understand is this 4 and this 9. Why 4 and 9? Those are strange numbers. It could be trying to find whether, say, 13 times that equals that or something. Whoa, suddenly we've jumped to 24. So that was an increase of 14. So each time there's an increase, it's adding that fourth number. So 1 was added, okay. Then 2 was added. Then 3 was added. Hang on, so it was 1, then 2, then not 3 wasn't added, then 1, 2, 7 was added. 1, 2, 7. 14. 1, 2, 7, 14. Let's make some notes here. So the left-hand number is 1 plus 2 plus 7 plus 14. So it's the sum of these numbers. These numbers are special for some reason. One 1055139. What are the factors of that number? What's special about that number? Two times 7 times 167 times 4513. 2 times 7 times 167 is 4513. Ah! It's the sum of all divisors, isn't it? 1 is a divisor, 2 is a divisor, 7 is a divisor, 14. Oh, okay. We'll leave it running, see what the next number is. So, okay, so what are the prime factors? 2, 7, 167. 2, 7, 167. 4513. So the sum of all divisors is going to be 1 plus 2 plus so okay, all divisors, so 1 times 1 times 1, 1 times 2. Okay, how do I organize these? So it's going to be 1 times 1 plus 1 times 2 plus 1 times 7 plus 1 times 167 plus 1 times 4513. Tell you what. I could write an easy Python script to do this, but there's sum of divisors calculators. Let's see. No point reinventing the wheel. Divisors calculator. Sum of proper divisors. Okay, so we want this number here. Sum of its divisors 18204.8. So it's including 1, 2, 4, 14, 167 up to the full number. Okay, so it's just that. So it's I still have it running. I should probably turn it off. Well, let's see. Oh, nice. Solved it just from the output and not from actually looking at the assembly code. Okay, turn it off. Let my fans, let my CPU cool down. That's an interesting problem. Would it be easier if I actually tried to reverse engineer the assembly code? I don't know. No, I think it would have been harder. I think the first part was just setting up the number 10551394. And then the process, I would have been able to work out this. It's a bit... I'm still not clear what that the 4 and the 9, the alternating 4s and 9s were. It's like, what's special about the number 4 and the number 9? Okay, well, whatever. Interesting problem, like, basically solved without code. Well, of course I used code, but the part 2 was kind of... had to use inspection. How did people find that? I think people found that hard. It was 19. It was harder. And many people didn't solve part 2.